I am very, very grateful to the organizers to have the opportunity to make this presentation on behalf of the MATISSE consortium. And I will, as I have been invited to speak about the instrument, I will speak quite a lot about the instrument. The MATISSE consortium is a quite big thing with a lot of people inside. Here I have copied extracts from the front page of the general paper describing MATISSE that we are supposed to submit in 1 or 2 weeks. So you have more or less a full list of the consortium members, and you have also in the affiliations the institutes which have participated. And I have slightly enhanced the 6 major institutes, which are the ones which are really giving substantial contribution in terms of money, manpower, etc., etc. And this is Côte d'Azur Observatory, Lagrange Laboratory, Leiden Observatory, the Max Planck Institutes in Heidelberg and in Bonn, and NOVA, which is a Dutch resource center, and of course ESO. MATISSE is a VLTI instrument. I will not discuss a lot about VLTI. I think it has been done. I just remind a few things that are useful to understand the following discussion about performances. So the resolution of MATISSE is the resolution of the VLTI at its wavelength. And in the slide, you see MATISSE and gravity side by side. And by the way, we will discuss also the fact that they collaborate as gravity being the fringe tracker of MATISSE eventually. We have 4 UTs, Macao adaptive optics on UTs, 4 ATs, Naomi adaptive optics on ATs, and this sets a limiting magnitude in the visible. Then there is beam transport, and there is CUDE lab guiding, which sets another limiting magnitude in the K-band, and then you arrive to gravity fringe tracker if you use it, and to MATISSE itself. So MATISSE is an LM and N band imaging spectro-interferometer. That means it observes from 3 to 13 microns with a certain distribution of spectral resolution modes, 2 low resolution modes in N and LM, a mode which is called high resolution in N, but which is quite moderate, it's 200. And then we have medium, high, and very high resolutions in the overbands, very high being 3000, medium 500, and high around 1000. And here on the right, you have a small selection of features, water, emission lines, and different components of carbonates and dusts. The AGN motivation, I think it has been discussed quite a lot in the conference and very well in the Leonard Butcher general AGN presentation. We basically know that the so-called unified model with a torus is not working very well anymore, even if it's still explaining that we don't see the BLR in safer 2 objects, and that we need to investigate quite a lot the structures, the inner structure of the dust, to understand how it works, to understand how the material goes in, how it goes out. And if we manage to constrain very well the understanding of the dust distribution, maybe at the very end of the road, you can even use dust torus parallax as proposed by Sebastian Hoenig to measure distances to the AGNs, which is quite exciting, but really needs to understand the morphology of this dust. The young stellar objects motivation, also it has been discussed quite a lot in the workshop. MATISSE will see a specific location in the dust disk in young objects, which is the inner part of the dust stream and certain specific characteristics of the dust. Here you have already one MATISSE image. I will come back to it. And this just shows the distribution of resolution covered by the different instruments and the very specific niche covered by the VLTI instrument from Pioneer to MATISSE. And when you are there, MATISSE is also strongly based on the heritage of MIDI, and this historical result from Royo and Bouquet, who basically show it by just changing looking at the coherent flux change, which means the difference between the spectrum at different baselines. That means resolution. You can quite strongly constrain the distribution of material in the disk and find out where are the different minerals and how they are transported, created, destroyed, and so on. Now let's speak about the instrument. MATISSE is a VLTI, it's an interferometric instrument, and it's in the mode what is called global beam combiner, which means that all the pupils illuminate the same focal plane. And in that focal plane, inside the airy disk, you have fringes. Here you see the pupils, you see that they are strongly anamorphosed, basically because you need much more pixels to explore the spatial direction, which is the one that contains the fringes, than to explore the wavelength direction, which is the perpendicular direction. On the right side, you see an image with the L band and the M band with dispersed fringes. And on the side, you see faintly the photometric channels, which are the one which allow to monitor the flux in the individual channels. Just below, you see the Fourier transform of these fringes, and you see the fringe peaks, so-called, each fringe peak containing the information of one baseline. And below, you see a cut of these fringe peaks. We have selected this global beam combiner solution for two reasons. We have studied in detail a pairwise solution for MATISSE because MIDI was a pairwise instrument. And we bumped into a certain number of difficulties related to cold optic components, size of the cryostat, etc. But we have also demonstrated that in the thermal background regime, a global beam combiner is the most efficient one, at least in a certain number of modes. In MATISSE, there are two modes. The one that we call A sensitivity, which is that we remove the photometric beams and all the flux goes into the interferometric beams because we just want to measure coherent flux. And the other one, which is called the simultaneous photometry mode. And in this mode, we have 2/3 in the interferometry and 1/3 in the photometry. And in this case, in this specific case, the coherent flux performance is as good as it would be in a pairwise instrument. The visibility in the N band will be slightly worse. So, sorry for the graph and the equations, but sorry. Is just to present the measurements that MATISSE makes and that the user can receive. The first measurement is the coherent flux, which is just the Fourier transform of the fringes. And you can average it coherently if you are able to stabilize the fringes, or you can average its squared modulus if you are not able to stabilize the fringes. Then from the photometric channels, you can extract the spectrum of the object. You can combine the coherent flux and the photometric channels to obtain the visibility, which gives the contrast of the fringes and basically gives the Fourier transform of the distribution of brightness of the object. You have the closure phase, which is independent from the photometric beams, and this is a quite important feature. And you have two other quantities which are independent or partially independent of the photometry, the differential phase, which is completely independent, which is a difference between the fringe position in a spectral channel of interest and the average spectral channel, and the differential visibility, which is a difference in contrast, which does not depend on the global photometry and just depends on the shape of the spectrum. On the right, you see a flowchart of how these measurements are made. From the VLTI, you have the fluxes, you have some detector cosmetics. The photometric measurements just directly allows to have the spectrum. The interferograms allow to compute the coherent flux. And then the combination of these two things gives absolute visibility. If you have fringe tracking, you can integrate the coherent flux, and then from it get differential visibility and differential phase, or you can do that a posteriori if your signal to noise ratio is sufficient by correcting the fringe position in each frame. And then you have all these measurements that are the individual measurements of MATISSE that you need to calibrate, and then you need to make the image reconstruction and to make the model fitting. I have mentioned it here in the lower part that there is a device which is called the near real-time software of MATISSE, which is basically the device that is used to acquire, to track the fringes. On the upper left, you have the image of the screen that you see, and here you have a more detail. On one panel, you have the dispersed fringes. On the left side, it's for a very bright object, so you see very strong fringes. These are not internal lamp fringes, so this is all really on the sky. Then you Fourier transform that in 2 dimensions, and you have the fringe peaks. And the fringe peaks are moving in the direction perpendicular to the baseline when the OPD is changing. And you track this position. What you have on the bottom is the waterfall, which is the position of each fringe peaks as a function of time. Here you see that it's very straight, so it's very well guided. On the right side, you see the same thing, but for a much fainter object, which is NGC 1068 on 80s. This is a 1 Jansky object. And you see that you are still fairly able to track it. So this gives you something like the limit, near the limit of MATISSE in terms of fringe acquisition and tracking. When you are able to use the gravity fringe tracker as a fringe tracker for MATISSE, this is called the GRAAMAT mode that we have just started commissioning just before the COVID shutdown. And it's now working on 80s and offered on 80s. And the very big advantage is that it allows to make long exposure images, which very strongly improves the SNR and also very strongly improves the spectral coverage. Because in the short bands in L and M, we have an away detector. To read the full detector takes more than 100 milliseconds. So if you are constrained by the, more than 1 second, excuse me, if you are constrained by the coherence time of the atmosphere, you can read only a very small fraction of the detector. For example, from all these lines, you can read only 1 line. What you see here in the middle are the dispersed fringes of BE star. On the top, you see the spectrum. You see that the L-band spectrum is extremely rich in hydrogen emission features. Here you have the bracket alpha line, a lot of Humphrey line, front lines. So you have a lot of emission line information. Some of them are also in the M band. In the lower panel, you have the visibility. The oscillation of the visibility is a signature of the fact that the object is it's a binary with a flux ratio of the order of 15. And in each line, you see a strong decrease in visibility, which corresponds to the fact that the gas envelope, which is producing the emission lines, is much more resolved than the photosphere of the object itself. And in the bottom, you see the differential phase. You see the typical, in the lines, you see the typical S shape, which is a signature of envelope rotation. And you see also the strong distortion near the end of the bands, which is due to chromatic OPD. And I will come back to that. This is one of the things that we still have to calibrate and to correct correctly. In the center of the bands, we are not very much affected by the chromatic OPD, but near the end of near the edge of the bands, it's a quite strong effect. And of course, this varies with temperature, humidity, and so on. So it affects the measurements. I am a little bit late, so there are other features that allow to reduce the noise, but I will go relatively fast. The multi-axial beam combiner reduces the contribution of the background because the background is not coherent. The MATISSE instrument is a spatial filtering instrument with pinholes. not fibers, because fibers were not available at the time of design. We are, of course, shopping. There is an internal OPD modulation, which allows to damp a little bit further the background. And there is a beam commutation, which allows to calibrate very accurately the closure phases. Very rapidly on this, when you inverse two telescopes, beam commutation means that you exchange two telescopes, then you basically invert the closure phase, which is in that triplet. And if you do that on the two pairs of telescope, you can actually invert individually all the individual closure phases. Here you have plots of the L-band closure phase. This is closure phase, and here this is wavelengths on the, but all these curves are calibrated. That means it's one calibrator minus another. And you see that on individual measurements, for example, in the blue line here, you have quite important instrument error on the closure phase. When you combine them using the BCD, which is two positions allow to have opposite signs on the source closure phase and the same signs on instrument. So when you make the difference, you remove the instrument. You see, and you see in the central line are the lines calibrated with BCD. And this allows to reduce very strongly the closure phase noise from something like, let's say, 1 degree or a few degrees to really a small fraction of a degree. MATISSE precision and accuracy. How do we measure it? We basically analyze three things: the fundamental noise, which is due to photon noise, background noise, detector noise, which gives an error per spectral channel, typically uncorrelated between spectral channels. We have global calibration errors, which are due to seeing changes, and which are broadband errors, fundamentally. They basically change the visibility of the instrument and also its closure phase marginally. And there are also broadband photometric errors, because we have seen that when you measure the photometry and you make errors, fundamentally what you see is the level of the photometry varying. And so you have basically a broadband photometric error, which impacts all the measures. How do we measure the fundamental noise? We take the measurements, we feed them with a polynomial to remove the broadband effects, and we compute the RMS of the residual, and we compare it to the ETC, the theoretical prediction. And actually we have very good fits for all fluxes, except at very high flux, where we stop to gain as a function of the magnitude of the star to hit a certain systematic level of noise. And on the panel on the right, you have these levels of noise which cannot be beaten in the instrument as it is now. It's a few fraction of a percent for the visibility, of the order of 0.1 degree for closure phase, and because of the chromatic OPD contamination of the order of 1 degree in L and M for the differential phase, it's much better in N with 0.2 degree. So this is...
You have 5 minutes.
Excuse me?
You have 5 minutes.
Okay, thank you very much. This is giving some, typically this gives a limit to the dynamics of MATISSE, of a few hundred in the L and M and around 1,000 in N with the instrument as it is now. The sensitivity to seeing changes. The seeing does two things. First, it changes the coherent flux of the instrument because it changes the visibility. And here you have plots of visibility as a function of coherence time and as a function of seeing. You basically see that you are strongly dominated by the sensitivity to coherence time. For example, when you have a good coherence time, the blue dots in the lower panel, the performance is almost independent from seeing. While when you have, even when you have a good seeing, if the coherence time is bad, then you have a strong sensitivity. And this gives a loss of coherent flux to the observer, and it has to take this into account when it computes its expectation. And then for a given object, we monitor the broadband calibration error by making transfer functions, which is variations of the instrument visibility with different calibrators as a function of time. and we either fit it or if we simulate the calibration science calibration to get the typical calibration error that we can have. And the panel here gives the values. In fair and good seeing conditions, the visibility accuracy is of the order of 2%. The closure phase accuracy is of the order of 0.2 or 0.3 degrees. And yeah, these are the broadband calibrations error which are implied. And then you have a last broadband calibration error that I mentioned, the photometric calibration error, which is basically analyzed by analyzing the variance of the photometry as a function of the flux. And we basically find that we have something like an additive systematic term of photometry, which can be converted in source Jansky. So for example, in the end band with 80s, you have a typical photometric error of 2 to 3 Jansky, and this strongly limits the possibility to have accurate visibilities. We combine all these measurements. We basically combine the fundamental noise estimate with the broadband calibration errors. These are variances that add, and this gives us a global line of performance that we can convert into numbers. At the end, we check the validity of this. I will skip this. These are the final numbers, which are the one which basically ISO offers to the user. And in red, I have indicated what the limit for the visibility. When you're able to do visibility, you're basically able to do everything, including imaging, if you have image reconstruction. And when you have only differential phase and coherent flux, you can do only some partial information. Comparison of MATISSE and MIDI is we are working as well, but MATISSE works very fast. I just want to finish on the imaging of MATISSE. We had a calibration, excuse me, a commissioning imaging run with a very good UV coverage that is indicated here. And the interesting thing is that we were able to reconstruct images during the run. This is a FSCMA Herbig star reconstructed image. Here on the left, you see what was reconstructed during the run. And here on the right, you see what was reconstructed now. So the image is much better, but and much more quantitative, etc., etc. But it's quite interesting to note that during the run, you are able to make an estimate of the quality of your imaging graph. To do, we have still quite a lot of things to do. GRAAMAT with UT is not commissioned, and we have to evaluate how GRAAMAT impacts the accuracy, which has not been done yet. We have to improve the internal tracking of MATISSE when GRAAMAT is not usable, and we have to work a lot on the chromatic OPD phase. And there is a bright prospect in the future if we are able to make off-axis tracking for MATISSE with GRAAMAT Plus, because the smiley that you see on the right of the screen, it's actually the sky coverage that MATISSE would have with gravity off-axis fringe track, because the isopistonic angle in N is quite large. Basically, thank you for listening, and thank you to all the people who participated in that adventure.
Thank you very much, Romain, for this really nice and clear presentation about MATISSE performance, and also congratulations to the team for putting together this instrument, because it's really not a small feat. So as you can see on Slack, there are questions already. I'm lost now. I think I missed the initial one about. Okay.
I see. Would it possible for MATISSE to retrieve?
Yeah, to retrieve closure amplitudes.
Amplitude. Normally, yes. There is nothing fundamental. We have 4 beams, so normally this allows to make closure amplitudes. We have not investigated the performance of this.
And then there's a question by about whether you can perform polarimetric observations.
No, we have a polarizing filters in MATISSE, which are installed just to eliminate wrong polarization effects from the VLTI. Actually, they are degrading the signal, and we are not using them. And they are not polarizing analyzers; they are just linear filters. So not really.
Okay, thanks. So there's a comment by Leo that says that you should probably ask ESO to make an announcement about FSCMA. The next questions, I think it's a little bit long, but we have 2 more minutes. You can read them all, Romain, instead of me, or you see the question by Lei Chen. While VLTI observation contains both fundamental errors and broadband errors, in the reduced data set from pipelines, there is just one number or uncertainty, which I believe is a combination of the two. Would it be possible to provide both parts of uncertainty in reduced data? I think this is essential for better interpretation of the data.
Yes, I think this is important also. The current error bars in the pipeline are just statistical analysis of the data itself. And this merges the fundamental noise and some of the broadband errors, and also actually amplifies the uncorrelated noise, because basically you have fluctuations like that, and really we have to separate that. It's possible. The tools that we use can be made available, and I think we have to work on that.